This is a little bit different. It's not something you see that often. This is my entire presentation. So you guys don't really have to read it. You can just listen to me. Basically, it's really great to follow that talk because who I am is Michael Prins right there. Yes, visioneering is a word I made up. I can do that because you can't stop me. There's my socials. You can look at it, but it's not going to help you because I am antisocial. Basically, my story kind of starts with I started working at Leaply, and we had a legacy app, and I took it over, and we started refactoring, and we started doing performance enhancements. And eventually I got to a point where we needed to basically change more of the app than we didn't need to change. And I had to make that probably the hardest decision that you'll get to make in your career is, do we rewrite it or not? And that's not going to be my talk. If you want to talk about that, we can talk afterwards. But I decided to rewrite it for many reasons. And when I just started to do that, you start facing all these choices. You get a blank slate. You can choose your language. You can choose your framework. You can choose your runtime environment. You can choose all these things. And these days, that's a difficult decision to make. I've been primarily a Rails developer for most of my career, and that's like kind of the easy choice. But there's so much stuff happening in deployment and in hosting providers. Serverless is a big thing. You have Docker coming to change the development workflow. And so I looked at all these options, and basically what I got to is, when you're building an application that you're not the only person that needs to work on it, you have to start making difficult decisions. You have to make decisions for other developers. And I tried to kind of take myself out of the situation and say, let me not look at what I know best. Let me look at what's going to work best for us. And I basically came up with these goals. I wanted to do two things primarily. I wanted to simplify development. So this is a very important thing. Like most of the time, your app runs itself, but you have to write the code. So I wanted a process that every day when I come to work and I sit down and I work on the app, I wanted that process to be as smooth as possible. And this is something that comes from Ruby and Rails, where things are optimized for developer happiness. And so that's something that I wanted to incorporate. But the big pain point for me was, I'm not a DevOps guy. I can do what I need to do when I need to, but the best day for me is one where I don't have to deal with a server. So that was something that I had. We had a bit of an issue. I wanted to do that as little as possible, and so I had to come up with a solution for that. So I'll take you through three things. One, what we started with. Two, what we ended up with. And three, my case of what I actually would have wanted to have, which, spoiler alert, doesn't exist. So we had a Rails app. A portion of the app was complicated. It was basically an app on its own. So we had a front-end Ember.js app for that. And we had the stuff kind of like muddled together. So you deploy the Rails app, and then we'd compile the Ember app, and then serve it from there. And we had a lot of background processes. We had a lot of queues and search. And so these things were kind of all put together on our own servers with scripts, Mina scripts and other deploy scripts. And the trick with that was if anything stopped working, it would be a mission to fix it, right? If you were the person who wrote it, it probably wouldn't be so bad, but I wasn't the person who wrote it. So that was something that I saw as a risk, and I wanted to get rid of that. So what we did end up with is we have a Rails API application. So our Rails app primarily serves JSON. It has a couple of exceptions where it serves PDF documents and so on, but for the most part, it's a JSON API. And we have a separate front-end application which is written in Vue.js, hosted on a CDN, which costs us nothing. And the only thing that we really had to do was connect those things using JSON web tokens and so on to make auth and so on work. But for the most part, scaling isn't a problem anymore. But there's some problems that comes with that. For example, trying to tell Google that a page is no longer available because you can't serve HTTP codes from your CDN, which we use Netlify, and they've actually recently added a feature that allows you to do that. So that's a little bit easier, but there's always these problems when you disconnect your app like that. What I actually wanted is I wanted to look at an application, and the pattern that you find in most applications, at least maybe not the really complicated, large-scale, complex applications, but the majority of applications that we as developers work on kind of follow the same pattern. And this is why Rails and a lot of these frameworks are so popular, because they kind of solve that problem for you once, and then you can just kind of follow the pattern and do it over and over again. But they do it in a certain way. And if you look at the new technologies like serverless frameworks and even AWS, if you in the previous talk, they're hosted with a cloud provider that's supposed to make you not worry about hardware because you don't own the hardware. And you saw all the stuff that they had to go through just to make that do what they wanted to do. There really isn't a smooth way to not think about hardware at all. And so that's what I wanted. I wanted to break down my application into endpoints. So our application is a series of endpoints. Each of them kind of do their own thing. The HTTP protocol is stateless. I mean, this is kind of how an application should work. You should be able to make a request, the code runs, and after the code is run, it doesn't need to stick around unless somebody else is making the same request. The closest thing that I could find to that is these frameworks that allow you to take something like AWS Lambda functions, whatever, embed your whole Rails application into them and keep spinning them up the more requests you have. That's the only way that you don't have to worry about how many servers you have, because they'll just keep giving you new servers. But to me, that didn't make sense. It didn't make sense to take this whole Rails app, which is this large dynamically loaded thing, spin it up to do a request and then kill it, right? It's easier from the perspective of you don't have to worry about servers, but it's very inefficient. The alternative to that would be, writing Lambda functions yourself. So take every endpoint, make it a Lambda function, and use whatever your platform gives you to hook those things up. Have the Lambda function be hooked to a HTTP handler or whatever, and do that for every request. And the problem is that pushes your development lifecycle out of your IDE or whatever it is that you're using on your machine, and requires every developer to go and learn some platform and interact with it frequently. So that's not what I wanted. What I wanted is I wanted to build an application, organize my code in such a way that it declares what the application can do, each endpoint, each trigger, each action, and have a mechanism whereby I can push my code to some provider, preferably using Git or something that I'm already using, and have it figure out what it needs to deploy and do the hot reloads, do the marginal deploys, everything like that for me, and do as little as possible. And the way that applications currently do this is exactly like I said. Oh, you spin up a new instance of Docker, you make it live, you do the load balancing, and then you turn the old one off. Even that, even though it works, I don't feel is the ideal situation. I think we've effectively split our applications up into very small units, and then we've made it that we can't separate them from each other, which doesn't make sense to me. I think if we've already done all the work to split our applications up into small units, we should be able to deploy those small units. And so I've kind of, obviously I couldn't wait for something to exist to do this, so this is why I ended up with doing the best I can at the moment. But this is something that's bothered me ever since I've started rewriting my application, is that this should exist. It's not technologically a reach for us to get. I honestly don't know why Google or AWS or so on haven't gotten so far as to give us this. But again, it becomes a trade-off. Rails is great. I love it. It's an opinionated framework. So if you like the way it does it, you're going to love it. If you don't like the way it does it, you're probably not going to. Unfortunately, there are multiple options, so you can find something that you like. But I thought, okay, if I could come up with something that worked for me, based on my experience of building applications from scratch, a lot of those patterns should apply to a lot of people, and we should be able to come up with something that works for us. And so I kind of started jotting down ideas and thinking about it, and started to think about all the things that I've worked with in the past, the technologies that I've enjoyed, that I found easy to use, and some of the things that I didn't like doing, and how I can have those things happen in a way that I don't have to interact with them. So what I've come up with is kind of a framework, but it's kind of a hosted provider. The way to think about it is if you had Heroku, which gives you a lot of these conveniences. You have a git push for deploy, it compiles your slugs, and it deploys it for you automatically. That's great, and it's worked for me in the past. But the problem with Heroku is once you get to the point where you have to scale up rapidly, that convenience charge that they have comes to a point where it's no longer feasible. For us, our application is based on user data, and we don't make our money from our users. So normally you would have activity, and that would mean revenue, and so you can pay for as many servers as you need to. In our case, that's not true. So I can't have 1 million requests a second and know that I'm going to make money to pay for 100 or 1,000 or whatever servers. So what I would like is something that rethinks the following issues. And these are just the core ones. There are other things that come with it. But the way I came up with a solution, if you would call it that, to this problem is by effectively not reinventing, but redesigning these things, the routing, the deployment, the templating, and the database in a way that facilitates them all working together. And this is kind of one of those things that you're always going to have. When you pick tools, you have all these options. And that's what's great about building applications in these days, is that you can pick your database, you can pick your framework, you can pick your hosting provider, you can pick all these things, but then the onus is on you to make them all work together. And fortunately for you, if there are 100 or 1,000 other people making the same choices as you, you have some corpus of information that you can use to make it work. But in the case where you don't, then that becomes either not an option or something that you're going to have to struggle with. So what I've done is I've kind of designed these components in a way that fit together well. And the core target of this is to have a framework and a platform that you can start using quickly. So you should be able to read a get started thing and within an hour have an application deployed to production. That's fairly easy for a beginner to understand. So somebody who's still a student should be able to do this in an hour, not just an experienced developer. And to make this happen, this is how I kind of thought about these things. I'm doing them in a specific order because they kind of, the design of the first piece informs the design of the second piece. So I'll work through it. When we're talking about routing, what I mean is that that part of the application deployment process where when you're looking to hit a page on your application, DNS points you to your hosting provider points it to your app, and your app figures out which page to render, and then it sends it, right? What I want to effectively do is split that whole system up so that everything happens at one higher level. So DNS would still go to your hosting provider, but rather than your hosting provider figuring out which app it is and your app figuring out which route it is, I feel if your hosting provider, if the platform does the routing for you so it knows exactly which page to serve, it gives us an advantage. It means that your application, all your code, all your endpoints don't have to be logically grouped together, which means you can split up your app into, if you say have 100 endpoints, you can split them up and they don't have to be together. They can be on different servers. They don't have to necessarily have all the same code in them. And that means when you do this bin packing that Kubernetes does for you, you can do those across servers on your whole platform for all different applications, which means if you bring an application in with one API endpoint and another person brings application in with 1,000 API endpoints, you don't necessarily know where they're going to be, right? Your one endpoint might be in between there, but you would benefit from having your endpoint sit on one of their, their servers, one of the servers that has their endpoints on it. And this allows us to move endpoints around. So if a specific server has a lot of load, you can actually, on a redeploy, pull an endpoint from that server and put it on another one. And you can look at the usage of the server overall and have ideal candidates for new endpoints. And you can do this every time somebody deploys. And so in order to facilitate that, you have to be able to separate the endpoints from each other. And in order to do that, you can't have a whole application like a monolithic Rails app available just to serve one endpoint. You actually have to use only the code that's necessary for that endpoint to function with it, so that you don't have this heavy thing that you need to move around. And this is unfortunately where we start to deviate a little bit from the Rails and the Ruby architecture, because Ruby is not good at this. Ruby is not good at taking a bit of code that moves around, because when you load everything, everything gets compiled, and you end up with this big thing that needs to be interpreted. So this kind of leans us towards something like a compiled language, and ideally something that does compilation optimization, or like in the JavaScript world, tree shaking. So imagine you have an endpoint that needs 1 or 2 libraries, and it needs access to 3 or 4 of your models, right? If you compile that endpoint, you require those files, and you would actually end up with a compiled program, i.e. a program that you can execute from the command line, that takes inputs, which your web server or whatever would pass into it, it would run, and once it's done running, it would end execution. So what would effectively happen, you would have, for example, a server with 1,000 endpoints, and these are command line programs available on the server, and as requests come in, they get executed, right? So you can do parallelism, concurrency, whatever you want to do to optimize that, and each endpoint is literally its own program. And because you can compile them, you have a binary, it's quick to deploy, and because you compile them, you can also you can hash them so that if dependencies change in your code, so say for example you have an endpoint, you don't change any of its code, but you update a library, right? When you deploy, that endpoint can be compiled. Once it's compiled, you hash it. If a dependency has changed, the executable will change, and therefore the platform can know that this needs to be deployed, right? It knows it's changed. It doesn't know how it's changed, but it knows it's changed. And that way, when you push your application, we can build everything, we can see what's changed, and then we can do a proportional deploy. So anything that's changed gets deployed, and that can happen in the same way that the typical Docker configuration would be, where you spin up a whole new instance, turn the other one off. What you would effectively do is you would spin up all the new endpoints on new servers or wherever there's capacity, and then you would update the load balancers to point to them. And when those old endpoints stop running requests, they would shut down. So you wouldn't have this issue if a request started and you do a deploy while the request is running, you don't have to worry about anything else. It would just finish and all new requests would go to the new one. And that would obviously update the usage on each individual server, and then the load balancing of endpoints would happen like that. What that allows us to do is when you deploy, you're effectively just deploying a whole bunch of files and some configuration. What that allows you to do is have that whole program. So in the case where the endpoint or the handler that you have is a HTTP request, you would just put configuration in that file that tells your application or the platform how to navigate to that. And then what the application platform can do is it can do kind of like Heroku has the mesh routing. It can do that on a endpoint level. So you end up with that radix tree routing for all applications on the platform, and you get to the actual handler of that endpoint faster because you don't have two separate sets of tree traversal. And then once we get to the point where we say, okay, well, we're compiling programs, and these endpoints are programs, you can do a bunch of interesting things like templating. I have this opinionated view that I prefer code that can run to render a view than a string file that needs to be parsed and then compiled and everything, because it gives you a whole bunch of advantages. If you look at something like the Lucky framework, where they have something similar to this, when your code is being compiled, there's a lot of static analysis tools that helps you with this so that you don't have unclosed tags or anything like this. And it also gives you the advantage of, if you're familiar with the front-end frameworks where you have the different components and you can reuse them, if your render function in your endpoint is just a block of code that runs, if you're requiring other files, so other components that have their own render code, you can compose them very easily, and each of them can be tested. So you could write your components, which are just view components that generate HTML or JSON or whatever it is. You can run unit tests on them or whatever, and then you can just require them in the endpoint that uses them. And then because you're calling them via your language, you'll always know that it will be valid. And because if it's a compiled language, if it doesn't compile, we'll know that it doesn't compile, and you won't have that issue. Another thing that I really wanted is, coming from, I spent a bit of time in the Clojure world, and one of the things that I love the most about Clojure is Datomic, the database. Now, explaining what makes Datomic awesome is a couple of other talks. But a lot of the things that Datomic gives you, I really like. I think it makes sense. But it's a little bit of a cognitive shift in order to understand how to use it properly. So what I wanted was kind of something in between what Datomic has and normal SQL or document-oriented databases. And I came up with an idea for a database that stores effectively semi-immutable data. And what it is you store effectively key value pairs. So an object is just a set of key value pairs and that are grouped together with an identifier. And that identifier would typically be something like a sequential ID that comes from the timestamp, so that it's not a 1, 2, 3 ID, but it's actually a UID effectively. And what that allows you to do is whenever you make writes to the database, you just write them, and they all go into a list effectively. And it effectively records the history of the object. So if you've ever worked in a Rails app and you've built a whole set of features, and then afterwards a client or your boss or whoever comes to you and says like, okay, now I would like to know when this thing changed and how it changed, right? And you either have to put in some gem that has a separate database table that just puts BSON objects in them or whatever to make track of that, keep track of that history. Something like Datomic does that automatically. And this could do the same thing. So it would just store all changes to a model. And the way that it has to then organize the data is very important, because what you would effectively have, or what my idea is for this, is that you effectively have one big database, right, that all applications share. So this takes care of that scaling problem, like, how big does my database need to be? When do I need to provision another one? How much throughput do I get, right? What we do is we create effectively, it's a ring database. So it has multiple servers and you can add to it, and data from different applications on the platform are ordered in such a way that data from the same application sits together, and data from the same object type, so effectively the same table, would sit together as well. And how you order these things are very important, because when you're doing a query, effectively what you're doing is you're traversing these keys. So if I'm saying I'm looking for a user with email address a@b.c, what I have to do is run through all the user objects, look at their email keys, and find the one that has that, and then look up the reference for that, and then I can get the object. In order to do that, I have to traverse it. And this is something that a SQL or relational database would do for you. So you would have SQL syntax to specify what you want, and it'll only return what you want. And in order to do this, where we have this auto-scaling database, what ends up happening is it's effectively a ring, and you add servers to it. And what they do is each server will have a boundary. So it knows what the earliest piece of information that it has and the latest piece of information that it has. And so when you request some data from it, it can tell you by a very efficient, basically integer comparison, whether that piece of information is on it or not. So you can send this request to each server in the ring, and the one that, any of them that has data, because you can't assume that one database is going to have it. Any server that has that data can then return it. And I've actually have a working example of this, but I wasn't ready to show, of how each database node balances its data, passing it between all the different tree nodes in it. And then they would do the same thing in the ring. So when let's say data that gets written to the database all ends up in one particular server, right? And you have 8 servers. You don't want one server that's 100% full and 7 servers that's 0% full. So what it does, it has a handoff mechanism, which is why it's in a ring, to hand off data to either end of its boundaries. So if it's full and the server next to it is not full, it pushes data towards that server on a regular interval to try and balance it. So you can write all data to one server, it'll eventually be spread out across all the different servers. And because data that's logically grouped from the same application get grouped together, if you start to have more data, the odds of your data being spread over more servers becomes greater. So if you're making a request to your application and you've got terabytes of data, those requests will be load balanced over 4 or 5 different servers. Whereas if you're a smaller application, you have very little data, maybe just a contact form, right? It'll likely all end up on one server, and all your requests will go to that server. So that gives you an automatic kind of like load balancing. But obviously, if you have a lot of data, there's going to be some performance impacts from that. What that also allows you to do is you can put a buffer in place. So each server maintains some kind of threshold. So let's say 75%. So every server is kind of the master for the middle 75% of its data. And the 12.5% on either side is actually a replica of what the other server on the left or right-hand side of it has. So the handover process of this server telling that server, I'm too full, this is now your data, is literally just moving a pointer and saying, oh, these 100 records or these 1,000 records or these million records are now your responsibility, and it doesn't actually have to send them over. That server already has it. It just updates its boundaries, and then over time when that load balancing happens, it'll be moving around the replica data. So the data that's moving around is always in one place. Most of the time it's in two places. And what that allows us to do is add a database server anywhere in the ring, and what will happen is it'll just be injected. It'll tell a master that this is your new left neighbor, this is your new right neighbor, and they'll start load balancing to it, right? Ideally what you want to have is you want that to be 50%. So the threshold should ideally be 50%. So there's the 50% of this server's data is the data that it has, and 25% on either side is the server to the left and the right. Now, if you have 25% of your data is half of the 50% of the server to the left, and the 25% is half of the 50% of the server to the right, all data is in more than one place, right? So if a server goes down, right, it gets pulled from the ring, but no data is lost. So now what happens is those two boundaries just get moved so that there's no replica data on those two servers. They'll start sharing the information that they have until you get to a point where they hit equilibrium again. And now if the server that went offline comes back online, it can't just go and shove itself in there. It doesn't, all the data that it's had is no longer relevant. It just gets added to the ring somewhere, it purges itself, and it takes the data from wherever it was added. And that's obviously the edge case. So 50% with 25% on either side means you have exactly 2 copies of everything. But then if you have 2 servers next to each other failed, and you have to deal with that problem. So more likely what will happen is 50% would be the maximum, and you would have something like a target of 30 or 40%, so that you always have these this leeway. And of course, in order to get to that point in an equilibrium state, all servers have to be at 50%. So if whoever maintains the platform ensures that servers are added when they're needed, this shouldn't happen. The key point here is whoever maintains the platform, not you as the developer. So you don't have this issue of like, is there enough space? Do I need to check on the whatever? The process allows for the platform to maintain that, and throughput to all the different servers should be maintained. So thinking about all this, what happens is the responsibility of maintaining resources falls to the platform, and this is effectively what AWS or Google Cloud or Azure is doing for you, is maintaining that. And then obviously there would be certain limitations. So like you would have regions. So you don't want an application in Tokyo requesting data from a database in Germany, and you're having all that overhead. So what would probably happen is you would have a region, you'd be in a region, the database and the app servers would all be in the same region. But you could obviously deploy your app in multiple regions, and then you'd have to do some kind of load balancing thing across that to do CDN type direction. One of the things that bugged me about the existing solutions is you could probably build this yourself or some subset of this on something like AWS. But these things get really complicated. Like for me as a software maintainer, I want pricing to be as simple as possible, right? I don't want to know how many requests, how much RAM, how much disk space, how much all of these things I have. I don't mind paying for them. I just don't want to have to figure out what I'm going to pay. So one of the advantages that this gives us is we can simplify the pricing model, right? So if you're using Lambda or Azure or whatever, they'll typically tell you you pay for storage space, you pay for requests, you pay for memory usage. And most of that is in place to ensure that you don't abuse the system, right? You don't want one person to benefit by using up all the RAM on all their servers and have them pay the same as somebody who uses almost nothing. But I think we can simplify this a little bit. If we set up the architecture in such a way, the way that the database works, the way that the deployments work and the routing works, we can make it a little bit more simple and charge for 2 things only. I think we can charge for storage and we can charge for activity. So each request or each megabyte of data, right? And the reason why we can do this is because of things like the database. So because it's a semi-immutable database, what will happen is all activity to the database gets logged, so we can bill you for all activity, right? So we don't have to charge you per write to the database or to read or per read from the database like Google does, right? We can just charge you for storage space on the database, and because all your activity creates storage space, we can charge you for that one thing, and it'll encompass your usage. Now, one of the things that you want to do is you want to be able to store those values and be able to bill for it. So if you have a monthly billing cycle, you would at the end of the month look at all the data, calculate how much space it takes up, and then bill for it. But you might not in your application want to keep all historic data of all your models, right? You might have a lot of temporary data that you don't want to keep paying for indefinitely. So you should be able to turn that off. You should be able to say, in your ORM, whatever you're using to persist the data, you want to say this model needs to keep history or not keep history. And what would happen if you chose not to keep history is the platform itself, so that's not something that you would have to do. You wouldn't have to write any tasks to do it. The platform itself would get rid of all data that has been billed for, taking into account what is the current values on your record. So if something was set on a record on your user, say 3 months ago, and you've been billed for it, it's not necessarily going to take it away because that's still the current data, right? It can get rid of history, but anything current it keeps. For other models where you want to keep the history, it can keep it indefinitely, and all that you have to worry about is how much space it's taking up, right? Because obviously space is something that costs every month, so you'd have to pay for it every month. But the ideal is that you just store this data and then you don't worry about it. There's a lot of extra things that we can do when we do this. One of the problems with storing data in this way is there's a lot of traversing data and a lot of processing that's required to build objects. And so the way that I envision that happening is the database would do as little work as possible. It would just stream these pieces of information to your application, and your application would be responsible for composing those into objects with or without history and making changes to it. But this is kind of ideal because now what we've got is we've got endpoints that scale by usage, and so you want that work to go to the instances that are handling the requests, not the database, because the database is shared and you don't want to put any extra load on it. You don't want to have complex joins that take up a lot of RAM and make who else is sharing your node of the database with you have their requests impact yours. You want that impact to be as small as possible. So what we can do is we can use streaming if we're using if we write the database and we write the framework and the environment, we can use binary packing for all our data. So we can make it as efficient as possible. And effectively, this ORM would be written by the platform maintainer, right? So you wouldn't have to write active record or the equivalent thing. You would get a library that gives you access to objects which you can create and define in your application. And you'd have your typical active record type of behavior like find, create, update that, and it would just do that behind the scenes. So it would know how to fetch the data, it would know how to composite them and make updates, right? So this is kind of great in a way because it's kind of Rails magic-y. You wouldn't have to know how it does it unless you wanted to. But it can also be a downside because you won't have the option to change this behavior, right? Like, the advantage is that you don't have to learn it, but you also don't get to learn it. So there's a lot of extra things that we can do with that. And if you want, you can talk to me. We're running out of time a little bit. So just a caveat, none of this exists. My plan is to write it if I can get around to it. But obviously, you can see what's involved in this. This is basically building AWS effectively, building Rails, building a database. There's a lot of stuff that goes into it. But I have started working on it. It's been very interesting. So if you're interested, come chat to me. I don't think we should take questions because there's a million questions that's going to come from this. So yeah, just come and ask me if you're interested in this, and I can tell you how it's going. Thanks.